Zaten kekili ama yavaş konuşuyorum.
Take your seats, except for Mr. Candidate, you are requested to keep standing. Esteemed candidate, you confront a committee which was appointed by the Council of Deans and that is charged with the task of examining both your dissertation and the propositions submitted therewith. Professor Bonzange, working at our university, will open the examination. Professor Bonzange, you can go ahead.
Thank you, Mr. Director. So, dear esteemed candidate, dear Veysel, it's nice to see you on this side of on the other side of the wall, in this case, and that you are defending now the thesis. So I have some questions, and actually I will start immediately to ask one question about the proposition. So I would like one of the paranyms to read proposition number 2, is possible?
Maybe you can stand up.
And then proposition 2.
Implementing advanced regularization techniques such as tailored batch normalization significantly improves the learning efficacy and generalization capabilities of models trained on small and imbalanced data sets. Thesis chapter 3 and 4.
Perfect, thank you. So my question is actually, you're using the words here to improve the learning efficacy and generalization capabilities. So how do you measure that? Can you say some words here? What is the right way to measure the fact that you are more efficient?
All are the opponents. So the learning efficiency of using any regularization technique to measure its impact on the generalization power of any machine learning model can be probably evaluated more by checking its confidence, if the model is confidence enough, or that is the first metric probably. But the idea to generalize further outside of the test data set is that it could generalize over the real world samples, outside even the outside of the data set distribution. Of course, the biggest problem with this is that if the data set distribution is different than the test set distribution or the training set distribution, the model will probably fail to generalize further. So to make sure that it can generalize further, we apply some regularization techniques to measure that it could generalize further, not just on the test set.
Do we have some metrics to measure that?
Yes, so generalization, so first of all, if we can randomly sample, what we do in the real world situation is that we usually pick some samples from the same domain and then measure its distribution similarity between the test set and then the real distribution, and then we try to measure if it's, let's say that test metric, we have F1, micro, macro, etc., and then we compare the accuracy level on that test metric, on the validation, and then the outside of out of distribution samples. But what we usually do is that we don't just check these metrics, we also check its confidence scores, that how confident the model is when it's assigning class A versus class B, because the average confidence distribution on the test set, if it is not same as when you get in the when you observe on the real world data set, this is probably a indication of the data set shift, or the data or the model is drifting. Either the data set is drifting or the model is drifting. So
I would like to remain a bit more on the metrics, because I see that in chapter 4 you use, for example, the F1 score, but in chapter 5 you use accuracy as a kind of metrics. So can you explain why this difference?
Okay. Since in both chapters I evaluated the model with different number of classes. If I use binary class, because the idea was in the first chapter, in the fourth chapter was to evaluate the impact of the batch normalization layer, and we only have 2 samples, healthy and unhealthy samples. So the F1 score on this is like when it comes to binary classification, it will be same as the F1 score. That's why to simplify the concept, I decided to stick to the accuracy, but I shared all the other like a precision and recall on each classes in the in my thesis in the papers published.
Okay, thank you. Then I would like also to move. We talk about 4 and 5. I would like to move to chapter 3, where you have give this list of technique approaches to learning with the small data. Well, actually, it means that you are asking for question for that, because if you have a list, then someone can always find something which is not in the list. Yeah. So I will do this. So I miss something about continual learning. Do you think a continual learning could benefit, or could benefit for the learning from, say?
Definitely, you are perfectly right on this topic. Continual learning is to let the model learn in a continuous way with the new samples, with the new predictions, so that the model can get a feedback loop based on each new samples. And then if we have, let's say that we have the same skewness as I explained in my thesis, like 1% versus 99%, which is what's happening in the real world situation. So if the continual learning, of course, in the first few rounds, even if the accuracy would be low, by learning, by feeding the feedback loop, it will probably improve the accuracy of the small samples, because the more the human expert rate these samples, and then the model will learn from human feedback, which means that it's going to improve way better than it was supposed to. It was at the beginning, even if the distribution, even if the skewness is the same. Right.
So I see I have to finish. Thank you.
Thank you very much, Professor Bonzanger. The examination shall be continued by Professor Emma Hart, who is online and working at the Edinburgh Napier University, United Kingdom. Welcome in Leiden this afternoon, Professor Hart. You can go ahead with your opposition.
Thank you, esteemed candidates. I just wanted to start by saying I very much enjoyed reading your thesis. I think it covers a number of very interesting topics. But I would like to start by, your thesis is about small data. So I would actually like you to start by defining what you mean by small data. And in fact, when does small data become big data?
How are the opponents? So small data, of course, it's a loaded term, right? So small data, actually, we don't suffer from small data. We suffer from labeled small data. So because of the real-world situation, most of the time the outliers, the rare events, are usually minority, even less than 1% versus 99%. So we usually suffer in the real-world situation, in the production environment. We usually suffer from the not having enough labeled data while we are annotating our dataset to build some predictive models. Even if we pick random samples in some real-world situation, we will probably end up with that rareness will end up in that training set as well. So that's why when we mean small data, we mean the human evaluated labeled data, the size of the data evaluated or labeled by the human to be used in a training sequence will be way lower than the other class, the majority class.
Okay. Is it possible to sort of quantify that? When you say it's way lower, do we mean like when the balance is like 90%, 10%? Or do you think there's a sort of threshold when it actually matters, when it becomes small?
So, of course, there are different techniques that I also mentioned in my thesis that you can upsample or you can gather more data to ruin this, to fix this imbalance, fix this skewness, of course. The first thing to do is that we generate synthetic samples, especially with the generative models. It's becoming easier right now to generate some synthetic nodes, but they will always have the same intricacies that the real-world samples will have. So it will not generalize further outside of its domain again, outside of its distribution. So even if we can upsample, for example, we can just upsample by using the embedding space. Rather than using the image itself, we can just get the embeddings of the image and then upsample so that we can generate new representation of the undersampled data, but it will carry the underlying latent representation of the small data. So that's a lot risky. So, but long story short, we can upsample, we can generate synthetic samples, or we can just use some other pre-trained models or the backbones to find new minority class from the real world situation. For example, in the real world project, what we do usually is that if we don't have enough samples, we use the primitive model to fish new samples that would come from that minority class in the real world situation, so that I can use that model as a proxy. Even if it's low, I can just, even if its performance would be low at the beginning, I can just use its confidence score or its precision or recall scores, especially the precision one, and then make sure that I can find new samples before doing another round of annotation. So those are the techniques we use because we have enough samples in the real world, but we don't have enough representation. You can just pick 1 million samples in an X-ray, for example, but 99% of the time it would be normal. So you would end up with wasting your time to annotate all these X-rays with no impact on the model accuracy.
Okay, so you talked a little bit there about generating new samples. So I think if you've got small data, there's several things you can do. You can change the architecture of the model, like you suggest in your thesis. You can generate synthetic data. There's also work in the machine learning literature that self-labels data, so you can have a machine label the data for you. So you chose to focus on mainly the architecture. Can you kind of justify a little bit that choice and why you perhaps didn't want to combine that with creating synthetic data or some sort of self-labeling?
So, especially the hype right now is like ChatGPT and GPT series. They are all autoregressive generative models. The idea was over there is that even if you have enough samples, if you don't have enough samples, of course in the self-supervised learning we don't even need any labels. We just generate new labels based on what we see in the unlabeled data set. So we generate some positive and negative samples in the generative models, for example, in the GPT example. So we usually cover like a hide or shade the next token so that the model tries to predict the next token all the time. By doing this, model tries to learn the underlying representation of the entire data set. So coming back to your original question, how self-supervised learning fits into the picture with generating synthetic data set. Of course, if we generate synthetic data at first and then try to create negative and positive samples out of this synthetic data set, I don't think it's going to help as much as you could do with the other techniques, because letting the model learn by itself with generating features by randomly sampling, randomly applying some self-supervised learning augmentation techniques especially, will be probably more helpful, which I already explained in my thesis, will be probably more helpful than using the synthetic dataset, because synthetic dataset doesn't have the underlying intricacies of that you could see in the real world situation. But if you apply self-supervised learning, this is going to generate new samples that you might see in the real world situation. That's why while we are picking the augmentation techniques, we usually pick the ones that could be applicable in the real world situation. You just don't add salting to any image if there is no salting happening in the real world situation, like salting like situation happens. So that's why, rather than generating synthetic samples, if you have a robust model architecture that could learn from self-supervised learning techniques, it would probably be more helpful than relying on the synthetic samples, because the more you use synthetic samples, at the end of the day, you will stick to what you have learned at the beginning.
Okay, so I think I've got time for one more quick question. So I think one of the interesting findings from your thesis is when you add this batch normalization layer into your architecture, you say that it reduces confidence in the output, but it increases accuracy. So I would just like you to comment in the remaining time, and to what extent do you actually think it's right to think of this output as confidence? Is it really a confidence in how sure we are about the classification, or is it mainly just a sort of function that basically tells us which side of a decision boundary it's on?
Okay, so when we say about the confidence, of course, we have limited tools to measure the confidence level of any neural network architecture. Over there, we were focusing on the softmax output that is fed into the softmax, that are the logics to fed into the softmax output. We noticed that when we add that final batch normalization layer, as you just briefly explained, it is impacting the accuracy on the minority class up to 60%, which was really surprising actually. That's why we named our paper unexpected. Anyway, so the idea over there, since we don't have the right tools when it comes to confidence evaluation, we use softmax over there, but we saw that the model is like a leveling off around 50 to 60% when we add that layer, which means that there is no way to measure if the model is confident or not. So which means that we had to end up with new confidence evaluation rather than just relying on that. So that's why we use some calibration score, we use some other techniques to see if the model is confident enough when it comes to assigning a certain class to that sample. I hope I could be able to answer your question.
Well, thank you very much, Professor Hart. I hope you can find it okay, the answers. The examination shall be continued now by Professor Pascal Kerschke, working at Technical University Dresden, Germany. Welcome at Leiden this afternoon. Professor Kerschke, you can go ahead.
Thank you. And first of all, esteemed candidate, first I would like to second the comments that Professor Hart already made regarding the nice quality of your thesis. It was really nice to read it. And well, to get started with my questions, I would like to ask you or one of your opponents to read out Proposition 5.
Proposition 5, can you? Proposition 5.
In machine learning, the imbalance in data classes significantly contributes to model bias, particularly affecting minority classes in fields such as fraud detection and rare disease identification.
Okay, thank you. So would you actually really say that the issue is on the imbalance of the data? Isn't it more like what kind of performance metric I use? So more or less coming back to the questions that we had in the beginning.
Who are the opponents? If I rephrase your question, when you ask that basically when I talk about the imbalanced samples, is there a specific way that means that I evaluate the accuracy or the performance of the model? Did I get it correct?
Well, I'm not entirely sure, so let me rephrase it. Looking at the imbalance of the data, you basically state that you can have some kind of model bias, but wouldn't the model bias basically just be posed based on the fact that I use maybe the wrong performance metric, like looking at accuracy or some other metric which does not handle imbalanced data?
Of course, when it comes to imbalanced data, our options are limited to use a certain metrics, especially the macro F1 score that is going to not going to overemphasize the majority class accuracy. That's why we like the first thing I check the macro accuracy. But in some domains, we also need to make sure that which metrics to improve further. Sometimes recall is more important than the precision, and as you know, sometimes the precision is more. So when it comes to a real world situation, like telling someone that you have a cancer is less risky than telling someone you don't have a cancer even if they have a cancer, right? So that's why, given the problem type, we pick some metrics to improve further, because there is not always we try to find a balance between certain metrics, but in some cases, apart from these classic metrics, we use some other how model is calibrated, because we are going to use this model in the real world situation. That's why if we see that the data imbalance is high and it's going to impact the model accuracy or the expected outcome in the real world situation, we always need to check like a confidence distribution or the model calibration by sampling again and again. That's why in the real world situation we use some feedback loops, and then we review, we monitor the model drift across different samples, so that if we see some shift in the distribution, we always try to annotate new samples and then train again, so that the model could be more balanced. Because even if everything looks good, when it comes to like a few months from now, we most of the time see this in the industry project, by the way. They come back and then complain about the model accuracy. That's why we do new annotation or use the proxy model to annotate further. So the long story short, yes, we are not just relying on a certain metrics, but we pick the metrics according to the problem type that we try to optimize further.
Okay. And should we maybe pick multiple metrics? Because you already mentioned recall, precision, and so on. So maybe some kind of bi-objective or multi-objective approach would be a better approach. What would you say to that?
So what we do is that, yes, you are right, so there are, but we do this before starting the training if there is any skewness or disadvantages over one class to another. But when we check, we sometimes try to, we change the loss function as well sometimes to make sure that the model would learn from the minority sample as well. And at the end, what we use is that we use the model confidence score versus the expected confidence score in the test set, and then try to see if, for example, let's say that I get 10 prediction with certain confidence scores at the end, and then I have some grantors. So I need to check if the model is being more confident while it's saying A versus be less confident while being saying model B. Right, that's why we try to label. We try to do some label smoothing over there, and then inject this formula into the training process so that the model doesn't try to just pick the right class, but also make sure that it doesn't go wild when it comes to assign certain prediction.
Okay, thank you. Then I have a question to another aspect of your chapter 3 on small data, where you actually state that humans are actually capable of learning new concepts from only few examples, whereas machine learning algorithms typically require significantly more examples. So would you actually say that humans are always better than machines and we just can get rid of all machine learning algorithms?
No, great question, by the way. So, of course, human learns not just from with their eyes. They learn from all their senses, all their background knowledge, all the previous experience. Even the 4-year-old kid, we know that we are not that level. Nothing, no model is at that level, even with the cat level, actually. So, of course, human can, if it's a human expert who has some enough experience, it can just classify certain objects with a few samples than any machine learning model, because the models start from scratch. So because it's like a kid born with some intelligent level. So the kid grow up and then he's usually has an advantage over the other kids above or average intelligent level, right? So which means that the kid was born with certain checkpoints, if I make a right analogy, with some initialization that could give him a heads up in the game. So what we do is that if you have enough experience or enough level or right initialization or right backbone parameters, you can learn from less samples because you already know what it looks like. When human assign a label, it uses all his senses and previous experiences and what he has seen. Of course, human could be biased as well because of the things that he has seen. If you are working in a hospital in the southern Netherlands, the ratio of the population will differ when you compare to Randstad area, as you know. So long story short, yes, human can do well because of all these factors that I explained. But if you have a right backbone architecture in the model that could already learn from all these samples and then already has seen enough samples, not enough, but already has seen enough, and then has the right checkpoint, when you just add a few labeled samples, it's, the learning rate, like the pace of learning will be much better than learning from scratch. That's why we are using transfer learning, we are using self-supervised learning, and then using the backbone that is trying through self-supervised learning to train another supervised classification model or segmentation model, because it's going to get a baseline rather than from scratch.
Okay, thank you. So just to double check, did I already run out of time? Or
yes, your time is more or
one
less
question?
up. Maybe a last remark, Professor Kess.
Okay, well, maybe then one very short question. So you suggested to pick the right approach, or you made a list of approaches to pick, like support vector machine, decision trees, Gaussian processes for a best choice for small data. And later on in your thesis, you focus on deep learning. So isn't there some kind of contradiction? So why would you say deep learning on the one hand and all the other approaches on the other? And short answer.
Yeah, that's another great question. Yes, exactly. Deep learning, when it comes to, if you want to benefit more from the deep learning, we need to have more data, because we saw that the more data that you dump into your training set, the model accuracy will be way better than if you have a machine learning algorithm with less data, right? But if you already have a right backbone, nice, right architecture with the right loss function, optimization function, and all the previous samples that the model already learned to change its during fine-tuning process. Right now, when you compare this approach with like 100 sample versus 50 sample with random forest versus deep learning, this approach will benefit more from the checkpoints, the already learned weights, more than the machine, because in the machine there is nothing to learn. You just start from scratch all the time. But deep learning, you transfer the knowledge across the different architectures. You can even change the architecture of the deep learning by keeping some layers intact or freeze or unfreeze and then use for the other purposes. The research says that this is much better.
I think we have to stop here, Professor Kerske. Thank you very much for the interesting questions. The examination shall be continued by Dr. Pelt.
Esteemed candidate, let me start by also saying that I really enjoyed reading your thesis quite thoroughly, as you may know. Of course, I also prepared a few questions. My first question is about chapter 4 and then page 91 specifically. So here you explain how you simulated an imbalanced data set for the experiments that you do in chapter 4. And the distributions of classes in the training set and the validation set and the test set are quite different. So the training set is very imbalanced, almost extremely imbalanced. The validation set is slightly less imbalanced. And then the test set is completely balanced. And I found that quite interesting, because in essence, you're then asking your network to do during inference, you're asking it to do something different than you ask it to do during training. And then apparently, yes, later you show that batch normalization in the last layer really helps in this case. It really improves the accuracy of on the test set. And I was wondering, so my question is my observation correct that you're asking the network to do something different during testing than during training? And can you explain why batch normalization then helps with this?
There are the opponents. Yes, so the reason for this is that I wanted to be cruel with the model, by the way, because I crafted this artificial, like synthetic distribution skewness, 1% versus 99%, and we had a nice data set, which is plant village data set. And then I wanted to create some skewness with as many samples as I have, that I can create this 1 versus 99 skewness. And I picked 3 plant types because of this reason, because those are the only one that I could also spare some for the test set and validation set. But as you already know, in machine learning or in a deep learning theory, it doesn't matter what you have in like any skewness in the test set or not, because it matters when it comes to evaluate the metrics. For example, if you have a skewness in your test set, the metrics that you need to pay attention is the one that we already explained so far, like a different thing, micro average or recall or precision, etc., so that you would pay more attention if the model is doing really well when it's come to minority class. But what we try to achieve here is that, okay, what matters for the model is the training set. It needs to learn from this skewness, but it doesn't learn from the skewness itself. It learns from the features that it learns from all these classes. And then in the test set, the model should do really well. It doesn't matter if the accuracy was 1% versus 90%. Because in the real world situation, if you have a unhealthy plant, even if you have 100 unhealthy plant at that day, the model needs to do really well compared to the test set, compared to the training metrics or the validation metrics. That's why I wanted to focus more on the equal distribution in the test set, because it doesn't matter for the model, because it's not learning anything from it doesn't even learn from the validation set, as you know. So it just learns from the training set, but we take the model that is learned in a very bad situation, very imbalanced situation, and then now it goes to the real world situation with everything is already normal. And then it needs to do really well. It shouldn't mess up with the performance that it already learned. So that's why I wanted to pick same number of samples, because it would be a new question. I know that if I had like 10% or 20% in the test set, and then the 80% in the like a majority class, I would always try to make sure that the accuracy on the minority class that I am always evaluating on the test set will be solid enough, will be robust enough, or scientific enough to evaluate the model performance. So it made my research easier to evaluate the model performance. So I just focus on the training dynamics rather than the test set evaluation metrics.
Yes. So why do you think then that the batch normalization works in this case?
Yes. So the batch normalization, as I explained in my thesis, is that smoothing the learning landscape of the model, because the Bayes normalization is removing the outlier activations while the model is learning. That's why we have Bayes normalization after each CNN layer in ResNet or VGG. But there was no study before that, right before the output layer. What if we normalize again? Because that is where the softmax is generating the so-called confidence scores. So our thesis is that when you have logits and then you apply another batch normalization, due to the nature of softmax algorithm, it is benefiting more the majority, like a higher number than the lower. So that's why it's trying to soften up or the leveling of the confidence scores, which we cannot use as a confidence anymore. So
do you see other ways of achieving the same result without using batch normalization, or is there something special about batch normalization?
Yeah, batch normalization is as I said, it is normal. It is increasing so that you can use large learning rates. You don't need to stick to the small ones, small learning rates, and then it reduces the outliers so that the model can convert faster. But why it is helping the minority class that much right before the output? So it's because of how softmax is designed. That was my initial thesis over there. Because softmax is not designed to evaluate the confidence, but normalizing the final logics in the last output. So why batch normalization is going to help in that? I couldn't still explain in detail, but as far as I see, the way that we use right now in the modern neural network architectures to calculate the final output layer or the softmax is not the way that can explain why batch normalization helps over there.
We have to leave it at that time.
Right.
Thank you.
Thank you, Dr. Mr. Candidate. There are more opponents coming. The examination shall be continued by Dr. Van Stijn.
Esteemed candidates, it was a pleasure reading your work. I would like to start with a very general question. So, reflecting on your work, what would you identify as the most challenging aspect conducting your research with small samples, and then how did you address this challenge?
Zeyler Doperens, can you repeat your last part?
Of course. So what would you identify as the most challenging aspect of your research with small samples, okay, and how did you overcome this challenge?
Okay. So the most unexpected and then significant maybe outcome is that we were trying to make the life harder for the model to learn from under high skewness. This is still a problem that is not being able to solve by even the high level, even the state-of-the-art algorithms as we see in the ChatGPT examples, right? When you try to ask something outside of your domain, you will end up with something different and you will never be able to know that if it's correct or not. So what we see is that my personal thought over there is that the one unexpected, we could still be able to deal with the situation by using the right architecture and by thinking outside of the box, by using, especially in my last chapter, we had to revisit like maybe 10 years old algorithm to see if it's going to help when it comes to generate new augmentation techniques, because when it comes to augmentation, we always focus more on the ones that we are always using in the research for the last decade. But when I revisited another algorithm that was designed for another purposes, it was really surprising for me to see that you can revisit the old algorithms and then apply into the modern architectures, and then you can use this as a proxy learning strategy to the modern architecture, so that you reduce your need on the labeled data set. So especially for the segmentation task, especially for the self-supervised learning, for example, when we try to, the data augmentation is the key ingredient of self-supervised learning, because there is no other way to generate the other samples that the model can learn from. You hide one part of the image, you add some noise, etc. But when you just, for example, another big one maybe, but as a human, when you say that you learn more from high resolution images, and you learn from low resolution images, if you want to zoom in and then try to detect something as a physician, let's say. But we noticed that when you apply these old techniques into low-resolution images, the model, and then use this as a proxy augmentation technique in the self-supervised learning strategies, the model tries to learn the outliers or tries to learn the useless information that it can learn. It's more like a generative models like right now. That is why we call it like a generative models as a blue JPEG of the entire world. Because it learns from all the tokens in the world and all the images in the world, and then it kind of zip them, compress them, and it's a compression actually, what we do in the deep learning. We try to generate a parametric representation of the entire world. So it was really surprising for me to see that with the revisiting the old techniques, applying it to model architecture, and playing with the different strategies, you can deal with real world situation, because this is how human can do inherently without even trying to do this on purpose.
Thank you. Yeah, so one of your contributions, this batch normalization layer at the end, you came up with this through your experience, your intuition, and through the research process, of course, of conducting various experiments. Now, on the other side, you also have a field called neural architecture search, where this kind of architecture choices we try to automate, right? Using perhaps some very large search space or different strategies. How do you think that this kind of methods could help also for small data sets? And would they come up, for example, with the similar conclusions?
So, these techniques, when it comes to, because like the reason that we had to play with these techniques is to see their impact on the minority class, of course, because we know that the model will always favor the majority class. But in some situation, as you said, even if the model even if there is no skewness, the model could still favor some of the classes, some of the samples more than the other because of what it learns, especially for the already fine-tuned models. You are right. If there is an inherent bias within the model that is already favoring the majority class. For example, let's say that we have some backbone, some metastasis detection model in a clinical settings. So if the model is already has some bias that is learned from some other distribution from the place that the model is deployed, it's probably going to favor that classes in the real world situation. So which means that, coming back to the original question, we can still use these techniques to make sure that the model doesn't negatively impact it from these kind of biases that is bringing from what's happening in the real world. Because in the real world, the rareness is the same as in the training set. So that's why even if it's a perfectly tuned model with a high accuracy, when you use this backbone to train another supervised model, you will need to revisit these techniques that we just described to make sure that it is not negatively impacted for the inherent bias that the model has.
You'll find it.
I have one more question.
Small one.
Small one.
Yes.
So these kind of biases, sometimes they are very hard to detect. How do you think, for example, XAI techniques could help in such a situation?
Exactly. So in the explainable AI, for example, we try to understand why model picks a certain class. So we try to see its activation map, we try to check its distribution, etc. So in this, by using this explainable AI techniques, we can always go back, try to reduce the impact of that bias, because there is always the trace of bias when you train, because you can just randomly remove some portion of the data. You can just cluster them, remove one of the cluster, and then test again to make sure that the inherent bias within the model can be removed by removing these samples from the data set. Because at the end of the day, you will probably end up with some useless data set, but then you need to go ahead. That's how life works. So you need to go ahead and then pick some new samples and then annotate them again to make sure that it doesn't. But if the bias is in the model, in the real world, there's a bias as well. But our job is that as a human, we can explain the bias if we have it. But in the model, if you trust too much the model, you will never be able to, it will slip by without even noticing. That's why there always needs to be some metrics to evaluate.
We have to leave it at this, I think.
Thank you.
Thank you very much, Dr. van Stein. The examination shall be continued by Professor Plaat.
Esteemed candidate, in your chapter 3, section 332, you mention AGI, artificial general intelligence, can you give a short answer to the question how AGI can help with data augmentation?
Oh, hello, the opponents. AGI is, right now everyone's talking about AGI, of course, so it doesn't actually help. We don't even need an augmentation if we achieve that level of intelligence, AGI, because in real world, I don't need, as a human, when I classify something, I don't need any augmentation to learn, because I already learned it. The reason that we apply augmentation is to introduce new samples to the model so that it doesn't just focus on what it sees, but it also can represent the entire picture that it is presented. In AGI?
You mentioned AGI in your thesis. And now you say we don't need it, we just need data augmentation.
No, I'm sorry if I articulated bad. So AGI, what I said in my thesis is that AGI, when we achieve that level of intelligence, the augmentation can be generated by AGI. But right now I'm thinking again, the AGI, when I have that AGI level, if I still have skewness and then I need to do augmentation, AGI can right now, as a human, I generate my samples, for example. So AGI can replace me?
Wouldn't it be harder to create an AGI? And what would you use as data to feed to the AGI?
So I don't think we will achieve AGI in our human life, probably. Because it's still not well understood as far as I see, and then we are not even close right now. The things that we see, if you have an educated eye, which we all have here, we will understand that it's not going to happen soon. But you can just represent what we have so far. But if you want to generalize further, even if you say that I achieved AGI, 1 year from now on, you will need to unless everywhere is loaded with some synthetic model-generated, AI-generated context that will repeat itself, so that we will have a huge problem in the future. I believe that too when we try to pick some samples to train new models, because it's going to use its own model that's already derivative of what it has seen before.
Okay.
So long story short.
So you believe that AGI will not happen in our lifetime?
I don't want to put my money on it, but probably I will not see it.
Thank you for this answer.
Probably I will not see it.
Thank you very much, Professor Plaat. The examination shall be continued by Professor Batenburg.
Esteemed candidate, I have also read your thesis with a lot of interest, and I want to expand a bit further upon the question posed by my colleague Professor Hart at the very beginning, namely what is the definition of small data versus big data in your context, and I want to make it a bit more complicated. Because, I come from the field of imaging, and we are very much aware there that data is a loosely defined thing by itself, and it can either be of very low quality or it can be of very high quality. So I can have noisy data or I can have very good data, and that matters a lot for my ability to learn and for my ability to generalize. So when you talk about a small set of annotated examples, it seems that you imply that the annotator is correct and that humans make no mistake. But if I have 3 doctors and ask them to outline a volume, or even ask the question, does this patient have a tumor or not, you might get 3 different answers. So how do you see the role of uncertainty in your data in defining this threshold between small data and big data, and how does it impact your results?
All other opponents, this is exactly what we see in the real world project right now. So whenever we see a project right now, because I sometimes work in industry projects, so we ask physicians to annotate same samples, three physicians. We pick some seed documents or seed images, data set, and then ask them to annotate, and then we evaluate their agreement levels. We see that they are usually not agree on each other because of all the things that they bring from their own perception, own backgrounds. So as you said, even if we have human experts over there, the annotated, the labels may not be correct at all. So most of the time, let's say that I achieve 90% F1 score, and then 10% usually comes from the, like half of 10% usually comes from the human label errors. So there are techniques to evaluate, to measure these errors in the human labels. What I usually do is that what I do is that I usually train a model with whatever I have but at first we make sure that agreement level is above certain level, let's say 70 or 80%, like 3 physicians. They all annotate the same samples. Then we start assigning them different samples from now on so that they can annotate on their own way the different samples, because we already know that they already work together, like a song together, right? So that they can understand each other, and they read the annotation guideline very well. Then we assign the different sample, and then we, at the first page, we train a model and then get a prediction on the same training set. On the same
Esteemed candidate, you have to stop. The time allotted to the examination of your dissertation and its propositions has passed. The committee withdraws in order to deliberate. I request that you and your company await our return here. Mr. Candidate, we have examined your dissertation and the propositions appended thereto. We have heard your defense and we have considered the report by the faculty concerning your previous study. On the basis of this, we have decided to admit you to the doctorate. Professor Beck is empowered to confer that dignity upon you in the customary fashion.
Volgaande aanvaardigde taak, mij door de rector magnificus der universiteit opgedragen. Uit kracht dan van de bevoegdheid ons bij wet toegekend, volgens het besluit van de commissie hier tegenwoordig, verklaar ik bij deze u, Veysel Kocaman, te bevorderen tot dokter. Ten bewijze hiervan zal u het diploma door rector, de secretaris en promotor ondertekend en met het grootzegel der universiteit bevestigd ter hand worden gesteld.
Fotograaf gaat naar voren komen. Nee, that's later. Photo first.
Having completed the duty assigned to me, I may be the first to address you as doctor and to congratulate you on the award of the dignity you have obtained. This honorable distinction is a well-deserved and highly valued privilege. At the same time, you are called upon never to lose sight of the obligations it imposes on you in the name of science and society. And I will hand it over to Dr. Schier, your co-promoter, to give the laudatio to you. Veysel.
Thank you. Dear Veysel, what a surprise we had when you approached Thomas quite a few years ago asking for a PhD position. You wanted to move to the Netherlands and get a PhD in computer science. However, you already had quite a great level of experience in the field and knew what you could work as a self-employed consultant. You took up the adventure, accepting a part-time teaching position at LIACS, working as a consultant and doing your PhD in parallel. In addition, you got your family over here and, together with your wife, raised 2 boys. Your achievements during these years are truly remarkable, and we are very happy to see that this part of your journey is now concluded by obtaining your PhD degree. Challenged with a full-time position at work and being a real family guy, you were truly dedicated to this path, taking every task so seriously. After we set the research question, you were taking it to the extreme and returning with so many extended results. In fact, you obtained one of the strong results by using imagination and creativity, digging an 10-year-old image processing method from the past and reviving it in the context of deep learning. We now call it deep creativity. Veysel, as you stand on the edge of defending your thesis, we want you to know that we have no doubt you'll succeed. Your persistence, intellect, and kind heart will pave the way for incredible things. Remember, the world needs your creative perspective and dedicated research. Congratulations on reaching this milestone, and here's to an even brighter future ahead. All the very, very best to you, Veysel, from Thomas and myself.
It's an agreeable duty for me, very learned doctor, to congratulate you upon your degree, also on behalf of the university and its Council of Deans. And before I close the ceremony, I will give the opportunity to Professor Hart to congratulate you. You are still there in Edinburgh, so you can look to the screen. I think she's there.
Congratulations. You should be very proud of the thesis and of the defense. I think there's so much interesting work there, and I hope you find some ways to take it forward and use it in the future.
And also Professor Keske maybe want to say a few words.
Well, also congratulations from my side. It was very fun to read the thesis and also to hear you, or to see how you defended yourself with all the different aspects that you now were challenged with. And well, congrats, and well, yeah, enjoy your party, hopefully.
Well, have a nice celebration today and a very good career in the future. Hereby I close the ceremony, and now you you can give the applause.